Hello everyone. In our early lecture, we studied about uh, some definitions on perfect square, square-free integer, some theorems related to tau and sigma functions, and some NBHM and net problems. In our current lecture, we'll start our lecture with the problem whatever we solved yesterday's lecture. So let's begin. Let's begin our lecture number 4. So here in this question they given we did the first part in our earlier lecture, so we will begin this lecture with the second part of this lecture. Here n is given 14. The prime factorization representation of 14 will be 2 into 7. So they asked us to prove that, to establish that sigma of n are equal to sigma of n plus 1. So as per our previous theorem, how we can find the sigma value, that we can write that the formula that sigma n equals to p1 k1 plus 1 minus 1 by p1 minus 1 dot p2 k2 plus 1 minus 1 by p2 minus 1 and pn kn plus 1 pr kr plus 1 minus 1 by pr minus 1, where p1 p2 and dot pn are consecutive, are the prime numbers of the prime factorization of the integer n. So here it is that n is 14. We have the prime factorization of 14 is 2 cross 7. So initially we have to find the sigma of 14, which is nothing but our 2 to the power k plus k1 plus 1, that means 1 plus 1 minus 1 by 2 minus 1 into product of 7 to the power k2 plus 1, that is 7, 1 plus 1 minus 1 by 7 minus 1. So if we look into it, we will have the answer, that is 24. Similarly, if we find out the value of sigma of 14, that is n plus 1, which is equals to 14, that will be sorry, n plus 1 is 15, that is 3 cross 5. So we'll find it out by 3 raised to power 1 plus 1 minus 1 by 3 minus 1 into product of 5 raised to power 1 plus 1 minus 1 by 5 minus 1, which will 3 square, that is 9 minus 1 by 3 minus 1 into 5 square 25 minus 1 by 4, where we will have the answer, that is again 24. So where we can easily show that sigma of 14 is equals to sigma of 15, which is equals to 24. That means our to establish that sigma of n equals to sigma of n plus 1 equals to 24, which proved our statement. So in the second case also, you can easily find the value for n equals to 206 and 9572. So I will show you the second way, the alternative way to prove the statement, the same question. So to show the alternative way, we can let me rub the page. The alternative way is quite similar. Without directly going through the formula, we can easily solve it out. That for an example, if we take the value of n equals to 206, I am writing that n equals to 206 and n plus 1 equals to 207. Obviously that 206 has the prime factorization, which will be 2 into the prime 103, and 206 plus 1, that is 207, has the prime factorization of 3 square cross 23, which is also prime. So to find out the sigma value, that sum of all the divisors of the number n, sigma of n will be our short, that is 1 plus 2, that is the k1 plus the number p1 into k2, which is also 1, plus the prime number. What is the prime number? That is 103. If we find out the product of these two, then we will have the answer 312. And similarly, we can add that 2 plus 3 into product of 1 plus 23, then also we can get the answer 312. So these are the two alternative. I think this alternative way, if any comparative examinations it comes that they ask you to find the sum of the consecutive divisors of a prime number, then only you must follow this property. Or in your college examinations, you can also find it out by this as usual formula using the sigma rule. So in our next slide, if we find out the theorem, whatever they asked, that in this our theorem they asked that tau of n is an odd integer if and only if n is a perfect square. So if they asked that tau of n, what was tau of n? Tau of n is the number of divisors of a function. So of a number of divisors of the integer n. So they asked that tau of n is an odd integer if and only if n is a perfect square. So they asked that n is a perfect square and tau of n is odd. We have these two statements. So it must be there that n equals to p1 alpha 1 p2 alpha 2 dot dot following pk alpha k. This is our prime factorization of the number n, integer n. Suppose we have we know that tau n is an odd integer, that our claim is n is a perfect square. In this place we assume that n is a perfect square, that only tau of n is an odd number. Now we can we did that tau of n equals to alpha 1 plus 1 alpha 2 plus 1 dot dot alpha k plus 1, which is the tau value of the integer n. If this is our n, then tau of n will be alpha 1 plus 1 alpha 2 plus 1 following by alpha k plus 1. Since tau of n is odd, because tau of n is odd, it is in our question, that in our theorem statement it is given that tau of n is odd, each alpha I plus 1, that is in every case for tau of n, that alpha I for all I belongs to 1 to k, that means in every case it is written that for all alpha I plus 1 I must be odd. Obviously I must be an odd number. Each alpha is an even integer, but we have our by statement that n is a perfect square, that must be alpha is a, or every alpha is an even integer. That means we can write it in the form of alpha equals to 2ki, that is for all alpha. And we have the prime factorization of n equals to p1 2k1 that p2 2k2 following by pk 2kk whole square. So in this statement we can easily write that n is a perfect square number, because in every integer prime numbers we have the square number. N is a perfect square. So conversely, if we suppose in our converse proof, we have to suppose that n is a perfect square. In our early part we proved that n is a perfect square, but in our converse part we have to show that we started our proof by taking that n is a perfect square. If n is a perfect square, that means there exists an m belongs to n such that n equals to m square. This is the definition of perfect square. That means there exists an m belongs to n such that n equals to m square. That means if we write the prime factorization also of m also, which is nothing but m equals to p1 alpha 1 p2 alpha 2 followed by pr alpha r and our n equals to p1 2 alpha 1 because n is a perfect square, p1 2 alpha 1, p2 2 alpha 2 followed by pr 2 alpha r, but so that we can write the tau of n equals to 2 alpha 1 plus 1, 2 alpha 2 plus 1 followed by 2 alpha r plus 1. So we can say that for each 2 alpha I plus 1 there is an odd if alpha I plus 1 is odd, we can easily say then tau of n is an odd integer. So in our next statement they asked us to establish the assumption which is below is if n we have the prime factorization of n is a prime, it is given that 1 greater than n sigma n and followed by the product of 1 minus 1 by pi. What by this, what is mean by this? This is mean by nothing but we have studied earlier that this means the product of 1 minus pi. That means pi is nothing but between 1 to r, that will be 1 minus 1 by pi p1, 1 minus 1 by p2 followed by 1 minus 1 by pr. This is nothing, this means this. Since the divisors of n includes 1 and n, that means we can write this sigma n is less than equal to n plus 1 is lesser than 9 n itself, because the divisors of n includes 1 and n, so that we can write what we can write, that is sigma n is less than equals to n plus 1 and less than n. So we can write it as the sigma of n by n which must be greater than 1. That means we can write n by sigma n, we are reciprocal both doing reciprocal both the sides. That means we have that n by sigma n which is this we can take this as 1, and if we write it in another form then we can have that in simplest form, that is 1 by n by sigma n. As per our well-known result of sigma, we already know whatever by using this we already solve in our early example to find out the value of sigma, that is sigma is nothing but p1 k1 plus 1 minus 1 by p1 minus 1 followed by pr kr plus 1 minus 1 by pr minus 1. So now this part is to we have to notice in every steps that n is written as n by sigma n equals to p1 k1 p2 k2 followed by pr kr is the product of primes. We can write n in the product of primes, and we have that sigma of n is the this we already know by our first theorem, whatever we proved in our first lecture to find the how can we find the value of sigma n. And in our previous slide also we wrote, and I told you that how can we find out the value of sigma n. So we can here we are taking p1 taking the denominators which is p1 minus 1 p2 minus 1 and pr minus 1 in upper side, and we have in our numerator, and we have that we are taking this to this, and we have pr this one this is the product of primes, and these are the denominator of our sigma function, and we are taking the denominator in the numerator. Then we have we are taking our p1 raised to the prime factorization in the denominator of our sigma function. Then we have that we are writing intentionally by p1 k1 plus 1 minus 1 by p1. Similarly this divides by p2 and this divides by pr kr. then we can write in the form of that p1 minus 1 by p1 k1 p2, this form. Intentionally we wrote this in the form of this. So but for each pi greater than pi minus 1 by pi ki, obviously for all I, and if we reciprocal both the sides, that 1 by pi is must be greater than by 1 by pi minus 1 by pi ki for all I. Therefore our result of n by sigma n is nothing but p1 minus 1 p2 minus 1 pr minus 1 by p1 p2 pr, and we are taking this as result number 2, and we have our result number 1 earlier slide, where which was this was our result number 1. I am writing the result number 1 here also, which was what was our result number 1, that was n by sigma n is must be less than 1, and here we have 1 minus 1 by p1 product of 1 minus 1 by pr. That means we can by 1 and 2 we can write it easily, that 1 less than n by sigma n. Then this one we can write as the product of I equals to 1 to r 1 minus 1 by pi. So here we write it that sigma product of I equals to 1 to r 1 minus 1 by pi. So here it is our it concludes our proof. I hope you does not have any misconception. So if we consider our move to our next slide, which is show that sigma of n factorial by n factorial must be greater than equals to 1 1 plus 1 by 2 plus 1 by 3 followed by 1 plus 1 by 9. So clearly 1 2 3 4 dot dot n are divisors of n factorial. We all know that. What is the factorial of 5 factorial means? 5 factorial means 5 4, the product of 5 4 3 2 1. So what that n factorial means? N factorial means that n factorial dot n minus 1 n minus 2 followed by 1. That means we can write that this purple line is only for understanding purpose. N factorial, that means which must be greater than equals to n. Then if we take the reciprocal of this, then we will have 1 by n factorial must be less than 1, because in reciprocal the obviously this opposes our early statement that n must be greater than equals to 3 and n equals to 1 2. This is for understanding purpose we wrote. That means for 1 2 3 4 dot dot n are divisors of n factorial, as 1 2 3 4 by 4 all are the denominator of n factorial. There are more divisors of n factorial, that such that n factorial must be greater than by n, and n factorial equals to n for n equals to 2. Now actually this statement we have from the known result. We have that sigma of ni by ni equals to summation d divides n factorial by 1 by d. That means we can write this as the form of this 1 plus 1 by 2 plus 1 by n followed by 1 plus n factorial. Here this arises because in our early statement we already wrote that, because before 1 by n factorial 1 by n arises or comes. That means which is nothing but less or equals to 1 plus 1 by 2 1 by 3 1 dot dot 1 by n, which concludes our proof. So if we move to our next slides, there is also we have an statement that if n greater than 1 is a composite number, then we have to show that sigma n then we have to show that sigma n is nothing but sigma, and this satisfies this statement. So here we have that we know that sigma n equals to the sum of the divisors of n. So we can write it in the form of this, and we have it is sufficient to show that it is for our sufficient to show that 1 plus d1 plus d2 dot dk must be greater than root n. What the statement actually says, I am giving you an example, because if we write that 1 plus 2 plus 4, which is nothing but the divisors of 4 have the divisors 1 comma 2 comma 4. So what will be the sigma 4? Actually sigma 4 will be the sum of all the divisors of the number 4. That means we have that 1 plus 2 plus 4, that is nothing but 7. So in this statement they told that sigma n, that means sigma 4 must be greater than 4 plus root 4. That means the value of sigma 4 must be greater than 4 plus root 4, that means 2, that is 6. And what was the value of sigma 4? That is 7. So this is our parallel example of our statement. So in our statement this only says, and which is I think you can easily solve, that n is a composite, then there exists a di such that di divides n. That means 1 this, that means you can write therefore we can easily write n divides n, and di is less than n. That means n by di. And also for any di greater than 1, we can write it in the form of 1 greater than 1 by less di less than, actually, and that means 1 by di is less than 1. That means we can write n by di is must be less than n. So thus we can say that 1 is less than by n by di must be less than n. This is our general sense. And anotherly we have that now di is greater than root n. That means 1 plus di is must be greater than root n. So we can easily say, what we can easily say by this statement, that sigma of n is nothing but, we can write it 1 plus d1 dot dot d2 dot d n. That means n plus root n, which concludes our proof that for any n greater than 1, there is a composite number which is that sigma of n greater than n plus root n. So if we move forward to our next theorem, so in our early theorem only we have the sufficient part, we doesn't the proof. Actually we need to prove the converse proof too. So we have we showed that n plus root n exists, but we now have to show the opposite part. We have to let me rub. Now suppose we can easily write that the reciprocal of di is greater than equals to 1 by root n. That means 1 by root n is lesser than 1 by di which says that n by root n is lesser than n by di. That means root n is must be lesser than n by di. So for dj equals to x by dj, and dj is a divisor of n, and dj must be followed that root n. That means sigma of n is must be greater than n plus n, which concludes our proof. Both the parties necessary to show this proof, because in our early statement we only says that n plus root n exists, but we have to but we in the question that they asked us to prove that sigma of n it must be greater than n plus root n, which we can need to show. Earlier we say you by the use giving example of root sigma 4 and n using n equals to 4. So now this is our statement of next slide, that find the form of all positive integers where n satisfying that tau n equals to 10. So what is the smallest positive integer for which this is true? So here they are mainly given us the things that for positive integer, that means n is a positive integer and tau of n equals to 10, which says that n is a positive. If n is a positive integer, that means n must be had a product of prime factorization. By fundamental theorem of arithmetic, we can easily say that that means with if n has a prime factorization, then must be n has the number of divisors which is tau of n. This that means they provide us the there is a that tau of n must be the answer 10. So if tau of n, if the result of tau of n is 10, then there is only two possibilities, only 10 equals to 1 cross 10 and 10 equals to 2 cross 5. These are the only two possibilities, because 10 has the divisors 1, 2, 5 and 10 only. So using these four divisors, the 10 only have the possible two combination of prime divisors, that is 10 cross 1 and 2 cross 5. So either this one happens and or this. So either k1 plus 1 equals to 0, that means 10 the power of 10 is k1, that means k1 plus 1 equals to 0, and nor 2 cross 5, that means k1 plus 1 into k2 plus 1, that is 5 cross 2 or 2 cross 5, which says that k1 equals to 4 and k2 equals to 1, and here k1 equals to 9. K1 equals to 9 means that tau of n must be followed by p1 raised to power 9, which is comparatively a greater one, which may be 2 raised to power 2 raised to 9. And in another case we have two values of k1 and k2, that is 4 and 9. That means we can easily write that tau of n equals to p1 raised to power 4 and p2. So if p1 raised to power 4, there exist only two distinct divisors, that is 2 and 3 we can write. That means 2 to the power 2 raised to power 4 into 3 and 3 raised to power 4 into 2. If we write both 2 and 3 consecutively, then in first case we have the answer 48, and in second case we have the answer 72. That since p1 and p2 both are distinct, that's why we wrote this in two forms, that p1 into p2, then another one is p2 into p1. So in the first case, that 2 to 2 raised to power 4 into 3, we have the smallest integer such that tau of n equals to tau of 48 equals to 10, which proves our statement, which satisfies our statement that tau of 48 which has the answer 10. Therefore 48 is the smallest integer, which said for n for to satisfy the value of for n, which satisfied that tau of n equals to 10. That means tau of 48 equals to 10. This is true for the smallest integer 48, which concludes our today's lecture. And so in our upcoming lecture we will conclude all the definitions of tau and sigma. So in our upcoming lecture I hope that will be our last lecture for to say and to satisfy all the necessary parts for tau and sigma, theorems, definitions, related examples, and we will also solve various example of net and NBHM problems, whatever is necessary and whatever will come in various comparative examinations laterly, or in our past PYQs, previous year question papers, whatever we have. So we will solve that also. So thank you to be here, and let's meet. I will meet you in our next lecture.